All right, welcome back, guys. So today we're talking about resonance and formal charge. When we're talking about resonance and formal charge, really all we're talking about is advanced Lewis structures. These are extra things that you need to do in order to make sure that your Lewis structure is correct. And let's go through it. First off, let's just go through and draw one Lewis structure. So let's go through and just draw the Lewis structure for this nitrate ion real quick. Now, remember, this is a nitrate ion. We're going to have one additional electron added into the mix. So we have 5 valence electrons for nitrogen. We have 6 for oxygen, but there's 3 of them, so that's 18. And then one more electron added to the whole thing to make it a negative charge. So if we look at that, we now have 24 electrons to play around with. We look at the different atoms, and oxygen is going to be the most electronegative, so it's going to be on the outside. Nitrogen is going to be the central atom here. And then we're going to have oxygen spaced evenly around on the outside. We know we're going to have at least a single bond to each thing. So now we have 1, 2, 3, 4, 5, 6 electrons that we have used. We're down to 18. We have 18 left. Fantastic. So we go through and we add 6 to each oxygen to give oxygen the full octet. Remember, oxygen is the most electronegative. It's the hungriest. And that is all of them. We are now down to 0. We check for octets. Oxygens are all fine. Nitrogen, though, only has 6. So we know what to do. We just take one of those guys, the lone pairs, and make a double bond. Great, and we're done. Except, are we done really? Because why did I choose this top oxygen? I could have chose these electrons with the right, or these electrons with the left oxygen, and did that. Does it really matter? So if we go through and look at 3 different possible structures for these ions, for these nitrate ions, we have 3 different things that it can go. Which one is correct? Well, the thing that you need to remember is that electrons are not static. They don't just stay in one place. They move. And in fact, these electrons that are being shared across actually move as well. What we have here, we have a situation where these electrons will move here and make a double bond, and these electrons will move back to become lone pairs. So then that leads us to a situation like here in the middle, where we have a double bond with the oxygen on the left and 3 lone pairs on the top oxygen. Well, we can just do that exact same thing again, right? Where we take these lone pairs, bring them down here, and these lone pairs come back up, and now we're in this situation. And in fact, we can just go back and forth between all of these 3 different resonance structures. These 3 different structures will just keep going back and forth, back and forth. So this happens very, very quickly, and you can kind of think about it as this has part of the same properties as a double bond, and it partly has some properties of a single bond, because part of the time we have it is a single bond, and part of the time it is a double bond. So it's constantly flipping back and forth, flip, 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 flip. So in this case, we have double bonds that move, and that's essentially what a resonance structure is. Or one way to know if you have a resonance structure or not is look for 2 very electronegative atoms that are connected to the same one. And when one of them has a double bond, the other one doesn't. So in this case, we have an oxygen and a nitrogen and an oxygen all connected together in a row. One of them has a double bond. It's probably the case where this will actually form some sort of resonance. Let's take, for example, this happens quite often, where you have this situation. Well, this is going to be in resonance with this structure. When you can kind of think of it as this double bond is jumping up around. Remember, the double bond isn't actually moving from here to here. That is not what's happening. What's happening is these electrons, this lone pair, makes a double bond, and this forces this double bond to jump back into being a lone pair. So that's essentially what a resonance structure is, what resonance is. One other thing we need to talk about is the idea of formal charge. Sometimes you can get some very, very complex Lewis structures, and multiple Lewis structures actually work. In particular, when we were dealing with d orbitals, remember those things in period 3 and lower can sometimes have more than 8 electrons in them. So how do you go about actually figuring out, does it have 8? Does it have 2? What's the deal with that? And the answer is by looking at their formal charge. Now, a formal charge is how many valence electrons do they have before the Lewis structure, and how many valence electrons after the Lewis structure. I'm going to give you an example with that just by looking at H2O. At this point, I think everyone knows the Lewis structure for H2O. You have oxygen with hydrogen and hydrogen. There is a bond here, and hydrogen or oxygen has 2 lone pairs. The rules are the number of lone pair electrons. So in this case, we have 1, 2, 3, 4 for oxygen, and half the number of the shared electrons. So it has 1 bond here, and since this is 1 bond, we're going to look at half the number. We're going to look at each bond, remember, has 2. So half the number of that is going to be 1. So 1 bond, electron from here and 1 electron from here. So it'll be 2. So the number of electrons after the Lewis structure is going to be 6. And you probably remember that oxygen typically has 6 electrons. So 6 minus 6 is 0. So the formal charge for oxygen is going to be 0. For hydrogen, what's the formal charge? Well, it has 0 lone pairs and 1 of the shared electrons, and typically has 1 valence electron, currently has 1 electron assigned to it. So 1 minus 1 is 0. Same here with this hydrogen. In this case, that formal charge on both of these is 0. And that's exactly what you want. That's what exactly is a stable thing. Let's go through and do something a little bit more complicated. So I'm going to look at 2 different Lewis structures here. And if you look, these are both valid Lewis structures. Hasn't broken any rules so far. For the sulfate ion, and this sulfate ion, in this one, it would be 4 bonds going to the sulfur. And in this one, we would have 6 bonds going to the sulfur. Normally, when you're looking at things, I always say use the KISS principle. KISS, K-I-S-S, keep it simple, stupid. It's an old saying. I think it's either Navy or a programmer thing. I can't remember. You would imagine you would go after the simpler one. This guy. It looks really simple. It doesn't break any rules. This is probably the correct thing. Until you start looking at the formal charges. So what is the difference between its charge normally with just as an element by itself, and what is the charge of it now with that it's actually part of a molecule? So let's go through and actually check this out. Remember, oxygen is typically 6. So here we have 1, 2, 3, 4, 5, 6 electrons for the oxygen and 1 extra one from the bond. So this is actually going to be a -1 charge because it has an extra electron than normal. And in fact, all of these guys are going to be -1, right? Because all of them have 7 electrons associated with them now while they're in the molecule, and before they would only have 6. So that doesn't work very well for them. And what about sulfur here? Normally it has 6, but in this case it has 1, 2, 3, 4 electrons associated with it. So in that case, 6 minus 4 is +2, or 2 plus. You can see here that we're kind of straining quite a bit on each of these atoms. They don't want to have more electrons than they need, or I'm sorry, they don't want more electrons than they normally have, and they want to have as many electrons as they have. And they want as many electrons as they normally have. So let's try this other one, where now we can go through and start looking at these formal charges down here. In this case, for this oxygen, we have 1, 2, 3, 4, 5, 6. 4 from the lone pairs, and then 1, 2 from the half of the electrons in the bonds. So 6 and 6. So this guy has a formal charge of 0. Great. This guy looks like it's the same thing as above, -1. Same for this one. This one, 1, 2, 3, 4, 5, 6, 0. And for sulfur, we have 1, 2, 3, 4, 5, 6. Sulfur normally wants 6, so it's 0. And you can see that this is a lot lower formal charges than this bottom one is a lot lower in formal charges than the top one is. So this guy is not the correct structure, and the bottom one actually is. But are we done yet? Some of you guys may have already seen this, but is this the full structure? Not quite. We have one more thing that we need to do, and that's, remember, resonance. These double bonds can jump and become 2 other double bonds. So this is going to be the full Lewis structure, including resonance with formal charge of a sulfate molecule. That's it for today. I will see you guys later.